Okay, welcome to our 7th Quantum PV colloquium. My name is Kara Stefan, and together with the co-chair Vamshi Katakuri, we will guide you through today's colloquium. Last year, Quantum PV was kicked off as the state initiative for quantum activities in Baden-Württemberg to pool all those competencies and to create an overarching umbrella brand that further strengthens these networks and makes them more visible. With this colloquium, we want to further promote the scientific exchange on quantum hardware and algorithmic topics in the field of quantum computing, to present the latest developments in this research area, and to promote the idea of co-development of quantum solutions. Yeah, and today I have the honor of introducing our speaker, Dr. Werner Dobrautz from Chalmers University of Technology, who came all the way from Sweden. So thank you very much for making the effort and joining us here today. Yeah, after a graduate study of physics at Graz University of Technology with a specialization in computational solid-state physics, Werner Dobrautz did a subsequent PhD in computational quantum chemistry in the field of stochastic wave function theory for strongly correlated electron systems at the Max Planck Institute for Solid-State Research and the University of Stuttgart. Currently, he is a Marie Sklodowska-Curie postdoctoral fellow at Chalmers University of Technology in Gothenburg, Sweden. His current research at Chalmers University and the Wallenberg Center for Quantum Technologies focuses on developing innovative quantum Monte Carlo methods and novel quantum computing algorithms to enable realistic electronic structural calculations for strongly correlated electron problems on high-performance computing hardware and current and near-term quantum computing devices. Yeah, and today he will introduce us to the topic of quantum chemistry as a potential new era of simulation and study. Quantum computing is emerging as a novel computational framework that can revolutionize various research domains. By using quantum bits, qubits, instead of classical bits, quantum computing potentially allows for much faster and more powerful computation than regular computers. However, current quantum computing technology has severe limitations, such as the inability to hold onto information for long, which we refer to as decoherence, errors in operations, the noise, and not having enough qubits to do meaningful calculations. In the first part of his talk, he will explain why computational quantum chemistry, the field of research that uses computers to simulate and study the behavior of atoms, molecules, and materials, in particular could benefit from quantum computing. He will also discuss the potential and limitations of state-of-the-art quantum computing approaches in this field of research. Yeah, in the second part, Mr. Dobrautz will highlight some of his research on novel quantum algorithms that allow meaningful chemical computations, even with the limited number of noisy qubits of current quantum computers. Yeah, and as always, questions can be posted in the chat for the online participants. And with that said, I hand over to you, Werner.
Thanks a lot. Thanks a lot for the very kind introduction. Thanks a lot for the invitation. So, yeah, not much more to say about me at my talk. I will today continue a little bit what Vamshi started in his first lecture to talk about quantum computing and especially how quantum computing could benefit the field of quantum chemistry. So the take-home messages I want to convey during my talk is, first of all, what is quantum chemistry? Why is it worthwhile? Then what is quantum computing, which of course was for you covered already yesterday and today by Vamshi and colleagues. And what are the potential advantages of quantum computing? And especially how can quantum computing help the field of quantum chemistry? And what are some of the state-of-the-art approaches? I will skip this, my introductory slide ahead after the very nice introduction by already. And here's the outline of my talk. So first I will cover the field of quantum chemistry and electronic structure theory. Then I will make the case for quantum computing, so to say. Why is quantum computing believed to bring a benefit, a computational benefit compared to classical computing? And especially how one can do quantum computing for quantum chemistry. And we'll finish with a conclusion and outlook of the field. So I will start off with highlighting that surprisingly small quantum systems are at the heart of fascinating physical and chemical processes. And I will start the motivation with one of the most important industrial processes of our time, which is the Haber-Bosch process, where nitrogen and hydrogen under extreme pressure and temperature are transformed to ammonia, which is a crucial process for current fertilizer production. However, as this strong triple bond of nitrogen has to be broken during this process, this process alone uses up to 2% of the world's energy consumption currently. At the same time, we have a biological pendant of this process in form of biological nitrogen fixation, where, for example, bacteria which live close to the roots of plants can't do this process under ambient pressures and temperatures. It is, however, not understood how this process is done in nature, and a full understanding of it would allow maybe the design of biocatalysts for a more efficient and greener production of ammonia for fertilizer production. While we don't fully understand this process, we can identify the important quantum mechanical systems which are responsible for this process, which in the case of this nitrogen fixation process is the so-called iron-molybdenum cofactor and other iron-sulfur clusters. However, an experimental study of these clusters and processes is extremely difficult, which is why we need the aid of numerical studies of these processes to understand the relevant electronic quantum phenomena behind these processes, to understand them and maybe design artificial versions of it. And this is not only restricted, for example, to nitrogen fixation, but many groundbreaking phenomena like artificial photosynthesis, high TC superconductivity, and also fields like drug discovery, material designs, battery development, and so on, require an understanding of small quantum mechanical systems. And it is important to have this accurate theoretical understanding at the quantum scale so that we can understand these processes and enable a bottom-up materials design approach to mimic these processes artificially. And this is highlighted, the importance of these processes is highlighted that around 30% of the current high-performance computing resources worldwide are used for solving chemistry-related problems. And how do we get these insights? The good thing in quantum chemistry and electronic structure theory is that we do actually have the equations at hand which govern these processes. And to gain insight into the physical and chemical properties like ground and excited state energies, chemical reactions, and so on, we need to solve the Schrödinger equation governing the behavior of these systems, where the current state of all electrons of our molecular systems is described by the wave function of the system, and all information of a quantum system in its easiest form is contained in the so-called electronic Hamiltonian, which is actually at the first sight not such a complicated thing to look at. Everything which it contains is a term which governs the kinetic energy of the electrons of our molecular system, then an attractive Coulomb force between the electrons and the nuclei, and a Coulomb repulsion term between the electrons of our molecular system. However, especially this Coulomb repulsion term correlates all electrons of our systems, and this term makes the analytic solution of this equation too complicated, and which then requires that we have to use approximations and computational approaches to solve these fundamental equations of our quantum mechanical systems. And depending on how accurately we want to solve this system and how accurately we want to treat the correlation, induces various methods and levels of theory to solve this Schrödinger equation. There are, for example, very efficient but not as accurate methods like Hartree-Fock theory or density functional theory, where this electron correlation term is only treated in the mean field, on the mean field level, which then, however, enables to study very large molecular system on this level. But the more accurate and the more explicit we treat this electron correlation term, increases both the accuracy of our method, but also the cost of our method, with the limit up here we have an exponentially scaling method if we want to exactly solve these equations at hand. And the idea of like quantum computing now is that we want to expand the reach of these highly accurate methods with a quantum computing and maybe a quantum computing with high performance computing approach. And we do need these highly accurate methods because these systems, for example, at the heart of nitrogen fixation, they are what's called strongly correlated. So this electron correlation term is very important. That's why we need highly accurate methods to get the correct theoretical insight and understanding of these systems. And now I just want to quickly sketch why does this exact method actually scale exponentially with the system size at hand. So in quantum chemistry, electronic structure theory, we actually usually not treat our molecular system in what's called first quantization or in a real space basis where we treat all the electrons and the positions of the electrons explicitly. But actually, we make an approximation that we use certain basis functions which resemble atomic or molecular orbitals, where each electron of our system can occupy these different orbitals of our system. And to make it easier, of course, since electrons are fermionic particles, we usually also have to take into account the spin of the involved electrons. And in essence, one of these orbitals can be occupied by a maximum of 2 electrons of opposing spin. And if we now treat this problem at this lowest level of theory, like Hartree-Fock theory, we end up with the lowest possible energy solution of these molecular orbitals without treating the correlation explicitly. But of course, this is not the only solution we get. So if we want to reach, we also get higher energetical resolution of these molecular orbitals in Hartree-Fock theory. And the more of these orbitals we use, the closer we get to this originally first quantized real space picture. And now, the exponential scaling of these electronic structure theory methods comes since we do not only have to consider this Hartree-Fock solution, where electrons only occupy this lowest molecular orbital, but we also have to consider all possible excitations on top of this Hartree-Fock solution, where electrons can also occupy this higher energetically and higher lying orbitals. So in the case of for hydrogen, for example, in a what's called minimal basis, this is like all still very treatable. We get 4 different solutions, which can be also efficiently represented in binary form, which then can be used on classical hardware very efficiently, where we only highlight which of these orbitals are actually occupied by an electron by the number 1, or if they are empty by a number 0. So for hydrogen in the minimal basis, we only get 4 of these contributions. But one can convince oneself that if our system gets larger and we have more of these orbitals to consider and more electrons, this quickly becomes gets out of hand. And the number of the configurations we actually have to consider grows exponentially with the number of orbitals and electrons of our system at hand. And already, like for small systems like F2, in a very small minimal basis, one already has 2 × 10⁹ configurations, which if we want to treat this exactly on conventional hardware, this already gets to the limit, and we already need up to 256 gigabytes of memory to store the wave function of such a small molecular system. And this is the curse of complexity, so to say, in electronic structure theory and quantum chemistry, that we have the equations at hand, but if we want to consider realistic systems, the computational cost scales exponentially with system size and easily and quickly gets out of hand. And this is where the hope of quantum computing for quantum chemistry comes into play, where the hope is that we can use the potential computational advantage of quantum computers to reduce the necessary computational costs to study large molecular system sizes. And what is the case for quantum computing? So why are quantum computers believed to bring this potential quantum advantage, especially for the field of quantum chemistry? So to start off again with the classical bits, like classical bits only can either be in the state 0 or 1, as you probably also heard yesterday already. And the novel thing about qubits, quantum bits, is that they can be in this linear superposition of the 0 and 1 state with appropriate normalization, of course. And if we look at, for one qubit, this can be quite neatly visualized in form of this block sphere, where, for example, a 0 bit is represented by an arrow pointing to the north pole of this block sphere. And we can also represent the action on these bits in this quantum circuit formalism, where we, similar to classical circuits, we can also, for example, apply a NOT gate to this initial qubit in the 0 state, which then will flip the bit, the qubit, to the south pole to represent 1. But opposed to conventional hardware, we can also rotate this bit around this block sphere and create this superposition of 0 and 1 states on quantum hardware, which is not doable with classical bits. Of course, if we then measure this bit at the end, especially, for example, in this superposition, it still will always like collapse to either the 0 and 1 state and yield 50% of 0 and 1 for this special outcome here. But the real magic of quantum computers comes, of course, if we bring multiple qubits together. If we not only have one qubit, but if we bring, for example, 2 qubits and also introduce what's called entangling states, where we have, for example, 2 qubit gates, like the C0 gate, which, depending on the state of the first qubit, flips the second qubit and thus introduces entanglement between our qubits. And as Vamshi has said in his talk today in the morning, one can also use this parametrized gates, where we not only have rotation of these qubits for a fixed angle around the block sphere, but with, as a function of some external parameters, theta. And the idea is now to use this quantum hardware to produce an approximation of this eigenstate of our Hamiltonian and to solve the Schrödinger equation essentially on quantum hardware. Where's the power behind quantum hardware? The power comes due to the possible due to the possibility of quantum hardware to represent an exponentially scaling state space. And for example, if we ignore normalization for now, but if we bring 2 qubits together, so 2 qubits are able to represent 4 different states at the same time. But if we extend this now and bring three qubits together, 3 qubits can already represent the linear combination of 8 different states. And you can convince yourself, and you know it probably, that if one brings together n qubits, one can encode an exponentially scaling state space of 2 to the n. And this is the potential what quantum computers can bring to the computational science. And for example, 40 qubits would already be enough to encode this 2 times 10 to the 9 states of F2 I showed you before, which is already at the limit of conventional hardware, of exact diagonalization on conventional hardware. But this exponentially scaling state space alone is not enough to bring quantum advantage, of course. We have to design and apply novel quantum algorithms to leverage this potential advantage and actually bring a practical advantage. And how one then why is especially quantum chemistry believed to be one of the fields where quantum computing can bring an early quantum advantage? And how does one treat quantum chemistry on quantum hardware? What one needs to do is, if we look back at these different configurations, how we describe our systems, like where we have our Hartree-Fock state and our different type of excitations on top of the Hartree-Fock space to describe our wave function, which describes the system, one needs to perform what's called the fermion to qubit mapping to represent our fermionic problem, since electrons are fermions, on qubit hardware. And what one does is we need to map our original Hamiltonian, but also the basis function we use to describe our system to quantum hardware and the qubits. And for example, qubits, the states of qubits, will then encode the occupation of these what's called spin orbitals used to describe our electronic wave function. And we then need to design quantum algorithms to, for example, target ground state solutions like the variational quantum eigensolver Vamshi was talking about, or also target excited states, dynamics of quantum systems, and so on. And let me walk you through this example here. So the idea of a quantum algorithm for quantum chemistry is that we prepare a certain initial state, for example, the Hartree-Fock state, where we apply these NOT gates to encode this Hartree-Fock Slater determinant, it's called, where electrons occupy two of the lowest energetically orbitals. Then we perform unitary operations of a chosen algorithm on top of this initial state, where the idea is that this unitary operation, for example, with these parametrized gates Vamshi was talking about, produce an approximation of the true ground state we are interested in. And then depending on the property we're interested in, we can then at the end measure certain observables like the energy, but also other properties on quantum hardware. And ideally, this would look like, for example, in the variational quantum eigensolver, VQE, that we have an iterative solution where we change these parameters of our quantum ansatz and get a nice curve where we end up after a certain number of iterations with, for example, the ground state energy of our quantum system at hand. However, you all know that even though we have this like fancy magnetic shielding, we are cooling down of our quantum computing hardware, still the effects of noise are currently quite severe. Like we can have all different types of noise that we have random bit flips, phase flips, decoherence between superposition of quantum states, and it all results in that these single qubit and 2 qubit gates, but also the readout of quantum information of quantum hardware is not exact. Like it has now quite high fidelity, but still if we want to apply like deep, long quantum algorithms, we essentially get random useless data if we don't do anything smart on top of it, of our current quantum devices. So in the near term, for example, the idea is to make use of the current quantum hardware we have to, for example, reduce the number of qubits or reduce also the number of gates and circuit depth we need to apply to get solutions to reduce the effect of noise, and also, for example, to devise error mitigation schemes which can reduce the effect of noise, and so that we can still get some useful results of current hardware before long-term error-corrected hardware will come to play. So in the long term, the hope is, and the promise is, that we will have error-corrected quantum hardware, which will enable also to have fault-tolerant hardware like we have now fault-tolerant classical hardware. And the idea, I mean, this is no room, I'm not an expert and I don't have time to talk about quantum error correction here. And this is also only a classical example, which does, of course, not work for quantum hardware. But the idea behind error correction is that we not use like one physical qubit to encode the information, but we actually use many physical qubits to encode the information on what's called one logical qubit. And for example, In classical hardware, one can use the repetition code, where one uses just many different bits to encode one bit. And then if there happens to be certain one-off errors, we can still, like on a majority decision, decide that this is still representing a 1 or 0 in the other case. And if we would have fault-tolerant quantum hardware, and this is also the promise why quantum computing can bring a benefit for quantum chemistry, there are algorithms which have a provable advantage in the field of quantum dynamics, in the form of the quantum phase estimation algorithm. And the idea behind the quantum phase estimation algorithm is that if we have a unitary operator and we have an eigenstate of this unitary operator, there exists an algorithm which can efficiently determine the phase or eigenvalue of this unitary operator. And maybe this reminds you of the Schrödinger equation, which is important for quantum chemistry, electronic structure theory, which I posted before, which has a very similar form. Although not in this unitary form yet, but we can, for example, look at the time evolution operator, which is just the exponential I times ht applied to a quantum state, which will then give us a very similar looking form, which will give us the time evolution of our exact eigenstate. And again, I cannot go into details of the quantum phase estimation algorithm here, but there exists a quantum algorithm which can then efficiently determine this phase if we have given this eigenstate and the unitary operator. And the idea here is just quickly that we have two separate registers of qubits, like we have one measurement qubit register and a qubit register which encodes this eigenstate. And by making a Hadamard superposition of all these measurement qubits and then performing controlled unitary operations of this unitary operator of on this eigenstate, one can encode the phase of this unitary operator in these measurement qubits in the Fourier basis. So one then still has to perform what's called the quantum Fourier transform, or the inverse of it, to then measure the phase of this unitary operator given this exact eigenstate. And the benefit here is that there is no matrix diagonalization involved. And since qubits can encode this exponentially scaling eigenstate, this has provable advantage over classical algorithms. And for example, it's also a subroutine of the famous Shor's algorithm for the Shor's algorithm. One problem with this algorithm, though, is, of course, how do we get this exact eigenstate? Usually, this assumes that we have our solution at hand already. So a problem is, for example, if we don't have an exact solution, but if we only have a linear combination, an approximation of the exact solution, we will not get the exact ground state phase, for example, but we will get a different phase measurement outcomes depending on the magnitude or the quality of our approximation to the ground state wave function. And as said, this is a fault-tolerant algorithm, so it requires many qubits, deep circuits, so it needs error-corrected quantum devices. And this problem of state preparation, like how do we get a good approximation of true ground state, is still a big problem for also the potential of the quantum phase estimation algorithm. And so currently we are in this intermediate regime, I would say. So we are almost past the NISQ regime, but we still have to deal with these noisy small quantum devices with limited utility, and we have to use hybrid approaches. But I do think it will not be a binary transition, as Vamshi also mentioned before, to the regime of fault-tolerant quantum computing, where we have provable quantum advantage, but it will be rather a gradual transition toward fault-tolerant. So the current phase and interest in quantum computing it's important to develop a certain intuition on quantum algorithm development, that we maybe also design algorithms now which can be transferred to the fault-tolerant quantum regime. And it's also important to provide feedback for the experimentalists of today and show and demonstrate them if their devices actually do what they intend to do. And it's also important to have this near-term utility and relevant applications. And importantly, I think it's also, there will be not a need for quantum for everything. So we will not need a quantum computer to treat all the problems on all the times and length scales, because there are efficient algorithms which can treat certain problems on classical devices to good enough accuracy. So the idea would probably be to use these quantum devices to study these strongly correlated small quantum mechanical systems embedded to target like larger relevant systems in the long run. So what are some current near-term approaches? And hopefully, if I have time, I will also sketch some of my and my group's work. So the idea of this NISQ era approaches is that we use the benefits of both quantum and classical devices in a hybrid manner. So the idea is to use a quantum circuit with the power to represent these 2 to the n states and use short-depth quantum circuits that fit current hardware and which can improve maybe on classical states and estimates by providing non-classical states on quantum hardware, with the power to store this quantum state with exponentially fewer resources. And for example, the prime example here is this variational quantum eigensolver. Vamshi was talking already about it, where the idea is that we use a quantum circuit parameterized with some parameters, measure the energy on the quantum device, and then use a classical optimizer to optimize the parameters of our quantum circuit in a self-consistent way to drive our solution to a hopefully good representation of our ground state of our problem. And for example, there are similar approaches like quantum imaginary time evolution. This is, for example, an algorithm I work with. But it has a very similar idea to have this variational and hybrid approach between quantum and classical hardware. But of course, as I said, this is not the current state, since due to noise, we only get these very noisy, non-usable results if we don't do anything on top of it. And for example, some state-of-the-art algorithms currently, one big idea many research groups globally pursue is to use quantum computers to enhance classically efficient methods, for example, quantum Monte Carlo methods. So if you remember this like hierarchy of methods, like quantum Monte Carlo methods are very highly accurate methods for quantum problems, which we have already. But they do have some computational bottlenecks. And the idea is to use classical high-performance computing to get a already good solution in form of using quantum Monte Carlo methods, but use quantum devices to then get the final accuracy which we need to get closer to the exact result. And for example, research teams both from IBM, also research teams from Beijing University and ByteDance, and the Google Quantum AI team are working on these hybrid algorithms to use a quantum device to improve quantum Monte Carlo methods, where, for example, IBM used quantum devices to improve Markov chain Monte Carlo, where the idea is if we have like a complicated energy landscape, to use quantum devices to propose more efficient moves in this complicated energy landscape, which are better than local classical updates. Or this team from Beijing University, they actually used quantum devices to improve Monte Carlo method I was actually working with at the Max Planck during my PhD, the full configuration interaction quantum Monte Carlo method, where the idea was to use basis transformations from like use quantum hardware to propose basis transformations to make this quantum Monte Carlo method more efficient. And the Google Quantum AI team used quantum hardware, quantum computers to improve what's called auxiliary field quantum Monte Carlo. And the idea there is to use quantum hardware to propose what's called trial states, which are better than classical trial states, to improve the efficiency of this quantum Monte Carlo methods. Another state-of-the-art approach currently is what's called subspace expansion methods, where the idea is instead of solving like this originally full Schrödinger equation, that we use quantum hardware to propose a different basis in form of some trial vector small psi, and then use quantum hardware to represent this psi, and also apply powers of the Hamiltonian to this trial wave function. And then use this new basis to create a smaller Hamiltonian, a smaller matrix, which then can be classically diagonalized. And usually this provides a very good approximation to the true ground state solution. So research teams from IBM and Riken in Japan use this or these types of methods to use quantum devices to create this like downfolded representation of the problem, which is then easily diagonalizable on classical hardware. And they were studying these transition metal compounds, for example, I showed earlier, these iron sulfur clusters with like very, very promising accuracy. And now, check the time. Oh, I have to hurry up a little bit. So my work currently was also concerned with this near-term algorithm, and essentially to focus on these different problem cases of near-term algorithms, like the restricted number of qubits, the restricted circuit depth, which quantum circuits and ansatz to use, and also the classical optimization. And due to the time, I will restrict myself now to a few approaches which concerned to reduce the necessary resources on quantum hardware, essentially. Because if we can make this quantum circuit smaller, we can, of course, also reduce the effect of noise of these faulty gates. And I will also shortly talk about a chemistry-inspired error mitigation scheme. So one of the reasons we need this many qubits to represent our quantum chemistry problem is what's called the cusp condition. And the problem here is that, for example, in real space, like if we bring two electrons together, actually the Coulomb repulsion between these electrons, if we bring them infinitely close, diverges, which then results that the exact wave function, the electronic wave function, has this very, very sharp feature if we bring two electrons together. And the problem with these basis functions is these orbitals we use in quantum chemistry to do the calculations, that they are usually very smooth functions. So they have a very hard time to approximate this very sharp feature. So we need many of these orbitals to actually accurately describe this very sharp feature of the wave function. And this is a problem for classical methods because it introduces this new axis of complexity. We not only have the system size our methods scale with, but we also have now this basis set size, how many of these orbitals we use. And at the same time, this is also a problem for quantum hardware, because the more orbitals we have, the more qubits we need to represent our quantum chemistry problem on quantum hardware. And an idea we were following also when I started at work still at the Max Planck is, why don't we use information on this very sharp feature of the wave function and make an ansatz for a wave function where we treat this very sharp feature with a function which is treatable classical on classical hardware, polynomial scaling, and then are only left with a smoother wave function which we treat on quantum hardware. And since it's smoother, we need less of these basis functions to get very accurate results with less qubits. And the idea behind this is that our original Schrödinger equation with such an ansatz, we can actually transform the Schrödinger equation and get a new eigenvalue equation with this easier wave function to look for, which is easier to represent with less basis function, less qubits, which means we have an immense resource reduction. And this is, for example, what we did in this work with IBM, where the motivation is to target this easier function and thus reduce the number of qubits and also circuit depth to get accurate results. And for example, we were able to study the lithium hydride. It's not the biggest molecule, but quantum hardware is restricted currently. But we were able to get the dissociation energy of lithium hydride on actual IBM quantum hardware to very, very high accuracy. While if we would not use this method, we would need hundreds of qubits to get the same accuracy, which is practically out of reach of current quantum hardware. And with a work of a PhD student of mine, we were actually able to reduce the circuit depth even further by not using a fixed ansatz function like this, which Bamchi was also introducing, but using what's called adaptive quantum Ansätze, where during the iterative optimization in VQE, we add certain gates, entangling gates, depending on some measurement and quantity. Another important point is error mitigation. So the idea is we know that we have error and there are different error mitigation schemes to reduce the effect of error by with some educated guess. And one method we were proposing is what's called reference state error mitigation, where the idea is that we use a state which we can classically compute efficiently, for example, the Hartree-Fock state. So we calculate the Hartree-Fock state energy, but also prepare the Hartree-Fock state on quantum hardware, which due to noise will induce this error in the energy measurement. And we can then use this error to mitigate a converged VQE calculation, for example, because we can attribute like the effect of this error due to the noise on quantum hardware, which will then be hopefully closer to the exact solution. And we use this, for example, on the Chalmers 3-qubit device, because at Chalmers we also are building our own superconducting qubit devices. And we use the 3-qubit Chalmers device to study again H2 in a minimal basis. So not the most exciting calculation, but it's only a 3-qubit device. But with this reference state error mitigation, we were actually able to mitigate this large error in blue and get almost close to exact results on this Chalmers device. And this method especially performs well when this reference state is close to the exact solution. So, for example, for H2, where we used only Hartree-Fock reference, this performed very well, like in this equilibrium bond distance. But if we stretch the molecule and like we get more correlation, the solution is farther from this initial reference, the effects are actually worse. So with a master student, we were actually working on extending this single reference error mitigation to using a multi-reference error mitigation and use multi-reference state, which capture like more of the correlation and get accurate results also in more strongly correlated regimes. I will skip this due to the lack of time and come to the conclusion and outlook. So the hope is that quantum computing can bring this quantum advantage for especially electronic structure theory, quantum chemistry problems, where we are interested in small molecular systems with strong correlation. And this will have a wide range of applicability in very, very important chemistry, but also material science problems like high-TC superconductivity, battery development, and drug discovery. And actually, I mean, 6 months ago, I would have been more pessimistic about this outlook, but there actually have been now some very, very exciting developments, both on the quantum hardware development, where of course, all the big industrial players have their quantum hardware roadmaps, but they're actually meeting their goals. So I mean, we have now the 1,000 qubit machine from IBM. with superconducting qubits, ion trap qubits, ion trap devices are pursued by Quantinuum and IonQ, with also like very, very promising developments. Then also like Pascal and Qera developing this cold atom quantum devices. And especially exciting was the recent development in quantum error correction development, where especially this year, I mean, and also this month or last month, there have been very, very exciting news with Google showing quantum error correction below the surface code threshold. There was this paper by the Harvard group and Qera where they used this cold atom devices to perform logical quantum gate operations. There's been recent development by the Amazon team with using what's called cat qubits to have hardware efficient error correction. And only a few days ago, quantum error correction for qubit codes by the Yale team. So it's, I think, a very, very exciting development, and especially this development of error correction and quantum hardware is very promising, especially for the field of quantum chemistry. And I want to acknowledge and thank my collaborators during the years, and also the funding agencies of my work. And I want to thank you for your attention.
Thank you, Werner, for your talk. You covered a lot of breadth, a lot of information, and
yes, maybe too much.
questions. Yes, please.
Thanks for the talk. I really don't know much about quantum computing algorithms, but this quantum phase estimation
Yes.
algorithm reminded or was analytically very similar to imaginary time evolution and projective techniques.
I wouldn't say imaginary time, is more to real-time evolution. So it's it targets what's called like dynamic problems. So it targets essentially to do this time evolution of a quantum system, so to say.
Okay. Well,
And to extract essentially the phase of this.
is there how severe is current sign error? Or
The sign error here?
Yeah.
I mean, actually not. I mean, if we could do quantum phase estimation, and I mean, more of the problems here are, as I said, how do we get this efficient representation of the exact solution? So we need a good representation of the exact solution. But then, if we would have error-corrected quantum hardware and enough logical qubits, theoretically, I mean, in practice, still, who knows? A lot of things can go wrong. Maybe there is like correlated errors which we still not know about of these quantum devices. But on theory, and if you can really prove it, that there is this exponential quantum advantage of quantum phase estimation.
okay.
So, but yeah, let's see.
Yes, you said it's necessary to have some representation of the eigenstate you want for the phase, phase estimation. But in Schroth's algorithm, actually, they bypass this problem by not knowing the eigenstate when they use the algorithm, but they know some other state very well, which is the uniform sum of the eigenstates. So in some cases, you don't really need the eigenstate to get some result from quantum phase estimation.
This is true. So in Shor's it works. So that's in Shor's you don't need it. But here the success probability essentially of your algorithm, and especially then for like larger extended systems, like then strongly depends on this. How close are you to your target state? Like how large is this coefficient of the state you're interested in this quantum phase estimation? So it's a different complexity class also, like this quantum dynamics and Shor's algorithm factoring. So yeah, I'm also still, I mean, if we have good hardware, we will also be probably able to get good estimations for the quantum state on quantum hardware to do this all like on quantum hardware.
Yes. Yeah. Thanks for the talk. Yeah, it's really nice. Are you using the entanglement property anywhere in the answers or in your quantum operators? Or?
For the work I'm doing?
Yeah.
Yeah, of course. I mean,
generally, I didn't get.
I mean, I didn't talk about these Ansätze and what. So as Vamshi said, I mean, in these hybrid quantum classical approaches, I mean, there are different. Essentially, you use the quantum hardware to make a good estimate for your ground state or your state you're interested in. And of course, you have to use entanglement here, because if you would not use entangling gates, you would not get like you would essentially get like classically easily simulatable states, which you're not interested in. But it depends. I mean, if you want to do like actual results on actual hardware, which in this work, for example, we did. I mean, we used the IBM device. There, you essentially need to use this hardware efficient Ansätze, where you're essentially restricted to the connectivity of your device and which types of gates you use. Because, I mean, yes, there are these different Ansätze, like Vamshi was mentioning, this unitary coupled cluster Ansätze, but they are usually, they have way too deep circuits for current quantum algorithms to make use of, because the noise is just too much in these. So, but you still have entangling and operations in these also hardware efficient Ansätze.
And the short questions in your slides 18, you have the wave function in Fox space, if I get it right. So here, yeah, sorry.
So this is, for example, one of these hardware efficient Ansätze, where you have like single qubit gates, for example, rotational gates around the y-axis, and you have these controlled NOT gates, 2 qubit gates, so which induces entanglement in your Ansatz.
But are you then using Fox space instead of Hilbert space?
Yes. So this is also kind of a problem of these hardware efficient Ansätze, that they don't conserve quantum numbers. So they can represent any state in the Fox space. That's totally true. And this can be quite a problem during optimization. So you also have to sometimes think about tricks to conserve and target the quantum subspace you're interested in. But you can do this, for example, with penalty terms, to not look at the full Hamiltonian, but the Hamiltonian with a penalty term, which then penalizes solutions with a different electron number, for example, or different spin. So,
Thanks.
Philip has a question.
Yeah, so somewhere on your slides you had this probability for this wave function for the success. So this looks like for strongly multi-reference problems you have less success with a quantum computer. Does this mean that you can also use things like basis set transformations, like using a CSF instead of Slater type determinants to improve?
This you mean?
Yeah.
But this is essentially, I mean, this is here, not here. This is not the best consistent use of math notation. Here I meant like essentially if you don't have the full exact wave function, you have a linear combination of eigenstates of H. So this represents eigenstates of H, not like any Slater determinants.
Okay.
So because if you have approximation to your ground state, essentially you have higher order solutions in your linear combination. So this is not like basis states, but these are estimated of phases of different eigenstates.
Okay, but then could you use a different basis set, like a CSF, to
Yes.
multi-reference?
Yes, no, this you can. And especially it's true, I mean, it's multi-reference, the strongly correlated problems per se will be more difficult, because there it's more difficult to get a good approximation of the ground state. So,
Okay, but since your work has primarily been on transportation, I guess you've mostly been using Slater type.
yes, but I mean, this is just an example of like a cube. This is like quantum phase estimations. I did not do quantum phase estimation. This is just an example. There is this algorithm which has this provable advantage in the field of quantum chemistry and structure theory.
I'll take this question first and then. So thanks for the talk.
I have two questions. The first one is quite related to that because so you are expanding the entire Fock space, right? So your particles number is not conserved, and you want to obtain a solution that is for a restricted number of particles that we usually do.
Yes.
Outside the quantum computing world. So, is there any way you can encode, for example, chemical potential in the Hamiltonian?
Yes, that's what I meant with these penalty terms.
Okay.
Yes. So you can, I mean, the thing is, I mean, if you're, usually the state you're interested in is like the true ground state of the Fock space. I mean, except maybe you do a Hubbard model or something else. I mean, there it can be different without a chemical potential. But in like quantum chemistry, usually the ground state is the problem, the true ground state of the Fock space.
Is
That's,
that a observation or?
Yes, of nature, I would say. I mean, that's like, it's all. But yes, you can still use these penalty terms. Also, for example, then to target excited states, you can use certain penalty terms to then target excited states.
Then the second question is, you mentioned something related to subspace expansion.
Yes.
You create some sort of subspace of the Hilbert space, then diagonalize it. Exactly. But so this power series of the Hamiltonian, in principle, allows you to expand the entire Hilbert space, right?
Yes.
So you just truncate it.
Yes. I mean, it's very similar to like classical or conventional subspace methods like power method, Landshaw's, Davidson. So it's like it's the same. You just, the thing is, you use quantum hardware since you have this advantage of being able to store an exponentially scaling wave function, and also maybe to be able to do this application of h squared more efficiently, and then maybe also to calculate like the Hamiltonian in this subspace more efficiently on quantum hardware.
So in that case, it's a term of a question of efficiency rather than accuracy, because you will always get a bias by truncating.
Exactly, you will have an error, you will induce an approximation, but the aim is to target such a big system which you would not be able to do with conventional Landshaw's or Davidson type methods.
Thanks.
We'll take the question from here.
Yeah, also, thanks for the amazing presentation. And so I'm from very different backgrounds, like medical, and when you said in the end you have hope for small molecular systems, so we might have very different ideas what's small.
That's pretty good piece.
I just wanted to ask, in your, if you say small, so how small is it? So like, can you be more? Is it like 1,000 atoms?
Nah,
or
way too big.
three, or
Way too big. dozen of atoms, like a dozen of atoms, I would say.
dozens?
Yeah, dozen. One or two. So essentially, these, for example, I would be quite interested, or like the whole field is interested in these type of, like these transition metal clusters.
Mm-hmm.
They're usually referred to, where you have, like, for example, here it's an iron-sulfur cluster, like you have some iron, some sulfur, and the thing is, you're also not interested in the whole space of these, but for example, you're only interested in the d shell orbitals of this iron,
Mm-hmm.
so you can restrict your space even further. But the thing is, I mean, usually I showed this exponential scaling on conventional, where, for example, with 18 electrons in 18 orbitals / basis functions, you're already almost above classical potential resources. So the hope is, I mean, there are approximations, approximative methods where you can treat like 50 electrons, 100 electrons in 200 orbitals and stuff, but it gets tough already. So, and for example, I think if you would have around 100, 200 good qubits, you could reach system sizes which you cannot handle efficiently classically. So there's this potential also for these near-term devices, which, for example, also the IBM, the IBM people with the, I mean, here essentially they looked at similar, like these iron-sulfur clusters, which, yeah, they used this 100 qubit device to study this.
And just, yeah, dozens of electrons.
Yes.
Yeah. So because you had this nice example in the beginning of this Haber-Bosch process
Yes.
for making ammonia, and the plants somehow can do it better. So are you going to find out soon, or?
Me, I guess not. I mean, maybe people will do, hopefully, but it will stick. I mean, the thing is, this is still only one piece of the puzzle then, to solve like this electronic structure of these small systems. I mean, it's also this these enzymes also, not all the magic is only these, but it's part of the magic. So then it's having like a good explanation of this, and then embedding, like treating this on a very high level of theory, like very accurately, and then maybe do a self-consistent embedding, because usually the larger molecular environment, you can efficiently and accurately treat on lower levels of theory. You can do density functional theory, and they usually will provide good enough energies for like molecular dynamics, etc. So the idea is to do it like self-consistently, use quantum to really tackle these strongly correlated, badly scaling systems, embedded with also maybe a high-performance computing, quantum computing hybrid to tackle the full problem.
So, and final quick question, and then to get there, because yesterday we heard very nicely overview about different classes of quantum computing hardware.
Yeah.
And like iron trap based and so forth. So for this kinds of problems you described here, is there a specific hardware class that fits especially well for what you're doing, or is it an open question about what you?
The hope is, at least in my research, to be hardware agnostic, like to develop algorithms which can technically, if the hardware can provide the necessary operations, that you devise your algorithms and then you compile it, like how we compile like classical computer code to hardware, compile it then to the certain quantum hardware. But my research is focused on this algorithm theory level and trying to be agnostic to hardware. But I still think, I mean, for now it seems like superconducting qubits, ion traps, and neutral atoms seem to be like the hot contenders. In my opinion.
Thank you very much, Werner. Due to time constraints, we'll have to stop here, but we can discuss at the coffee break. He's available here for questions. I'll hand over to Chiara.
Thank you. Yeah, thank you so much, Werner and Vamshi, for the insights and also the discussion. In our next colloquium, we will have Professor Joris von Slageren from the University of Stuttgart on site, presenting his experimental work on molecules for quantum technologies. And further, you can also meet Quantum BV and the various partners and their research activities at the upcoming Quantum Effects Fair on October 8th and 9th. If you want a free ticket, please reach out to our Quantum BV office via the displayed email. And with that said, I thank you for your attention and have a nice afternoon.